In 1931, a 25-year-old Austrian proved that mathematics cannot prove everything that is true. Worse, he proved that mathematics cannot even prove that mathematics works. And he did it using mathematics. To understand why this matters, you need to meet David Hilbert. In 1900, at the International Congress of Mathematicians in Paris, Hilbert stood up and listed 23 unsolved problems. The second one was this: prove that arithmetic is consistent. Prove that the rules of mathematics never contradict themselves. Prove that 2 plus 2 will never equal 5. This sounds obvious. It is not. Hilbert wanted a formal proof, built from axioms, with no assumptions and no hand-waving. He wanted mathematics to verify itself. A system that could look in the mirror and say, "Yes, I am sound." Here's what Hilbert was really asking for. A formal system is a set of axioms and rules. You start with statements you assume are true, and you apply rules to derive new true statements. Like a machine. You feed in axioms, turn the crank, and get theorems. Hilbert wanted 3 properties. Consistency: the machine never produces a contradiction. Completeness: every true statement can eventually be produced. Decidability: there's a procedure to determine if any given statement is true or false. If you could prove all 3, mathematics would be done. Settled. Finished. A perfect clockwork universe of truth. Kurt Godel was born in Brno in 1906. By all accounts he was quiet, meticulous, and slightly terrifying. He read Russell and Whitehead's Principia Mathematica, a 2,000-page attempt to derive all of mathematics from logic. And he noticed something. A crack in the foundation. What if you could make mathematics talk about itself? Self-reference is the key to everything that follows. Consider this sentence. This sentence is false. If it's true, then what it says must hold, so it's false. If it's false, then it's not actually false, so it's true. It's a paradox. It loops forever. Philosophers had known about this for 2,000 years. The liar's paradox. Amusing but harmless. Godel's insight was that this wasn't harmless at all. It was a weapon. And he could aim it directly at Hilbert's program. Here's the trick. Every symbol in formal mathematics can be assigned a number. 0 gets 1. The successor symbol gets 2. Plus gets 3. Equals gets 4. Every formula is just a string of symbols, so every formula becomes a string of numbers. And every string of numbers can be encoded as a single number using prime factorization. 2 to the power of the first digit, times 3 to the power of the second digit, times 5 to the power of the third digit, and so on. Every mathematical statement has a unique number. Every proof has a unique number. Mathematics becomes a game played entirely with numbers. And number theory is mathematics. So mathematics can talk about its own statements. It can reason about its own proofs. Godel had built a mirror. Now he constructs the sentence. Using his numbering scheme, Godel builds a formula whose Godel number encodes the statement, "This formula is not provable." Read that again. The formula says, about itself, that no proof of it exists within the system. If the system is consistent, what happens? If the formula is provable, then what it says is wrong. It says it's not provable, but we just proved it. That's a contradiction. The system is inconsistent. If the formula is not provable, then what it says is true. It really is not provable. But we can't prove it. So there's a true statement that the system cannot reach. The system is incomplete. Either way, Hilbert loses. Consistent means incomplete. Complete means inconsistent. You cannot have both. This is the first incompleteness theorem. The second theorem is worse. Much worse. Godel showed that if a consistent formal system is powerful enough to describe basic arithmetic, then it cannot prove its own consistency. The statement, "This system is consistent," is one of the true statements that the system cannot prove. Mathematics cannot verify itself. It cannot look in the mirror and confirm that it works. It has to take its own soundness on faith. Hilbert's dream didn't just fail. Godel proved it was impossible. Not that we haven't found the proof yet. That the proof cannot exist. The reaction was immediate and devastating. John von Neumann, arguably the smartest person alive, had been working on a proof of consistency. When he saw Godel's paper, he stopped. He told colleagues there was nothing left to do. Hilbert, reportedly, was initially furious. Then quiet. Russell called it a serious blow. The entire formalist program, the dream of perfect foundations, collapsed in a single 25-page paper. Let's be precise about what Godel did and did not prove. He did not prove that mathematics is broken. He proved that no single formal system captures all of mathematical truth. 2 plus 2 still equals 4. Calculus still works. Bridges still stand. What he proved is that there will always be truths that sit outside any given set of rules. No matter how many axioms you add, there will always be another true statement just out of reach. Truth is bigger than proof. That's either terrifying or beautiful, depending on your temperament. Godel moved to Princeton in 1940. He became close friends with Einstein. They walked to the Institute for Advanced Study together every day, Einstein reportedly saying he came to work mainly for the privilege of walking home with Godel. But Godel grew increasingly paranoid. He believed people were trying to poison him. He would only eat food prepared by his wife, Adele. When Adele was hospitalized in 1977, Godel stopped eating. He died in January 1978, weighing 30 kilograms. The death certificate listed the cause as malnutrition and inanition caused by personality disturbance. But the ideas survived. Alan Turing read Godel and invented the Turing machine. The incompleteness theorems led directly to the theory of computation, to the halting problem, to the architecture of every computer you have ever used. Godel showed that mathematics has limits. Turing showed that computation has limits. Together, they drew the boundary of what can be known. So here is what Kurt Godel proved, in plain English. Any system of rules powerful enough to describe arithmetic will contain true statements it cannot prove, and it cannot prove that it won't contradict itself. Mathematics is not broken. But it is, and always will be, unfinished. The map can never fully capture the territory. And the man who proved it starved to death, afraid of the world he had so precisely described.